In a dark room, a beam of sunlight slips through a tiny hole and throws a perfect upside-down image of the outside world onto a wall. 1,000 years ago, a man under house arrest used this simple trick to change how we understand sight, light, and science itself. His name was Ibn al-Haytham, known in Latin as al-Haytham, and his story is as much about curiosity and courage as it is about optics. He is born around the year 965 in Basra, in today's Iraq, a bustling city of scholars and traders. From the start he is drawn to patterns, geometry and tile work, glints of light on water, the way shadows stretch and shrink during the day. He studies theology, mathematics and philosophy, but he keeps coming back to a question that had puzzled thinkers since antiquity. How do we see? Before he can answer that, history sweeps him to Cairo, capital of the Fatimid Caliphate. Word has reached the Caliph that this scholar from Basra claims he can tame the Nile with engineering, a grand idea to regulate the river's devastating floods with a massive dam in the south. The Caliph summons him. Ibn al-Haytham travels upriver, studies the terrain near Aswan, and realizes the project is impossible with the tools and materials of his age. Now he has a problem. Saying no to a ruler famed for sudden whims can be dangerous, so he feigns madness. The authorities place him under confinement in Cairo. Confinement becomes a laboratory. Stripped of public life, he turns a room into an experimental workshop. Lamps, polished metal mirrors, vessels of water, thin screens with pinholes, rulers, strings, and notes upon notes. It is here that he rescues vision from 2,000 years of mistakes. Most ancient authorities had imagined that vision happens because the eye sends out rays that strike objects, sight as a kind of touch. Ibn al-Haytham flips the explanation. Light, he argues, travels from luminous sources and bounces off objects into the eye. We see because something reaches us, not because we reach out. He sets up careful trials, cover one lamp among many, and the corresponding spot of illumination vanishes. Block the path and the image disappears. Change the angle and the reflection moves exactly as a billiard ball would. He emphasizes straight-line travel of light and uses the pinhole to show that each point on an object sends a ray through the hole to the opposite point on the screen, producing an inverted but sharp image when the opening is small. He studies the anatomy of the eye from available medical texts and observations. He describes the cornea, the crystalline lens, and the transparent humours. He knows the eye does not shoot rays out, instead it receives them. He reasons that the surface at the back of the eye, the sensitive layer, must be where a structured pattern of light lands to produce sight. He doesn't have modern retinal imaging, but his reasoning is closing in on the right structure, and his camera obscura experiments make inversion of the image plausible. Crucially, he separates physical optics from psychology. The eye receives a map of light, but the brain interprets it. His book on these studies, 7 volumes on vision, light reflection, refraction, and visual perception, becomes one of the most important works in the history of science. He writes with a precise method: define the problem, review what predecessors claimed, state doubts, set up an experiment, measure, analyze, and only then draw cautious conclusions. He is blunt about authority. The searcher for truth, he writes, must suspect even himself and critique what he reads, because error can hide in subtle assumptions. In an age that revered classical authors, this is a quiet revolution. Reflection first. He proves that the angle of incidence equals the angle of reflection with geometric reasoning and experiment. He studies curved mirrors, spherical and parabolic, and asks a beautiful, difficult question. Given a point source and an observer, where on a spherical mirror will a light ray reflect to connect them? That challenge, later called al-Haytham's problem, leads to an equation of high degree and anticipates ideas from analytic geometry. He cannot solve it in general with the tools of his time, but he maps the terrain so clearly that later mathematicians return to it for centuries. Refraction next. He knows that light bends when it passes from air to water or glass, and he measures how the path changes. He compiles tables and describes how denser, media slow light's passage, bending rays toward the normal. He does not capture the modern sine law of refraction, but he pushes observation much further than anyone before him, insisting on numbers, not just diagrams. From refraction, he leaps to rainbows and halos, to mirages shimmering above the desert, to the way a stick seems bent in a pool. He dissects illusions, noting not just physics, but also perception. The moon looks larger near the horizon, not because of refraction, he argues, but because our mind judges it farther away, and so unconsciously magnifies its apparent size. He explores after-images, apparent brightness and contrast, laying groundwork for vision science. He applies the camera obscura, literally a dark chamber, to astronomy. During an eclipse, he projects the sun's crescent through a small aperture and studies its shape without damaging his eyes. He criticizes aspects of Ptolemy's astronomy and optics, objecting when models explain phenomena with mathematical tricks that seem physically impossible. Over and over, he demands that our explanations of the heavens and of light be not only calculationally useful, but also plausible in the world. When the caliph who confined him dies, Ibn al-Haytham regains his freedom. He spends the rest of his life in Cairo, supporting himself by copying manuscripts, teaching and writing. His output is immense: treatises on optics, mechanics, astronomy, geometry, and the philosophy of science. He writes about centers of gravity, balance and equilibrium, and the nature of motion. He composes doubts on Ptolemy, pressing for physical coherence in cosmology. But it is the Book of Optics that travels farthest. Centuries later, his writings are translated into Latin and circulate under the name al-Haytham. European scholars seize on them. Roger Bacon quotes him, Witello builds on him, and Johannes Kepler, grappling with lenses and telescopes, moves the image from the lens to the retina, an idea illuminated by al-Haytham's one-way light-into-the-eye reasoning. The new science of optics, from Renaissance painters experimenting with perspective to physicists analyzing lenses, grows with his work as a cornerstone. The camera obscura becomes a tool not just for study, but for art, and eventually a path to photography. What makes Ibn al-Haytham so modern is not only what he said, but how he said it. He treats error as a teacher. When an experiment disagrees with a revered author, he does not bend the experiment. He questions the author and the setup, then refines the test. He is patient, meticulous, and willing to be wrong in the service of getting closer to the truth. He is also humane. He writes clearly, warns against overconfidence, and urges a kind of intellectual humility that still feels fresh. Do not trust a claim because it is ancient or beautiful. Test it. Imagine him at night in that room in Cairo, a lamp flickering, a bit of smoke rising from the wick. He holds a polished metal mirror at different angles and watches a spot of light slide along a wall. He records the positions, draws triangles, calculates, frowns, tries again. He stretches a string to mark a straight path, then blocks it with a screen pierced by a single needle hole. The world outside, houses, windows, a narrow street, appears inverted on the far wall, sharp and miniature. He is delighted not because it is mystical, but because it is precise. Each point on the outside scene sends rays in all directions. Only those that can pass through the tiny hole arrive. Fewer rays mean a dimmer image, but also a crisp one. Widen the hole and the image brightens and blurs. He writes it down. In the morning he might visit a scholar to debate Ptolemy's models. In the afternoon he might copy a text for income. In the evening he returns to the pinhole, the glass vial, the angled mirror. Day by day he builds arguments that would endure for a millennium. He does not have our lenses, our telescopes, our detectors. He has his eyes, his hands, and an insistence that the world be interrogated with care. By the time he dies in Cairo around 1040, he has done something extremely rare. He has shifted both a field and a mindset. He has ended the I-beam myth and established a physical account of vision. He has shown that experiments using simple tools can arbitrate between competing theories. He has given later generations mathematical problems rich enough to stretch their skills. And he has left a message that crosses centuries. Knowledge grows when we commit to method, measurement, and honest doubt. If you step into a dark room today and poke a tiny hole in the window shade, you will watch the outside world bloom on your wall. That little inverted cityscape is more than a neat trick. It is a portal back to a scholar who, under pressure and constraint, chose to turn his confinement into discovery. It is a reminder that science isn't born only in grand observatories or shiny laboratories, but also in quiet rooms where someone asks a good question, tests it carefully, and writes down what happens. Ibn al-Haytham's legacy is everywhere. In the camera in your phone, in the lenses of your glasses, in the method scientists use to separate signal from superstition. He taught us to see, both literally by explaining vision and figuratively by showing how to look at the world with disciplined curiosity. A millennium later, we are still living in the light he helped us understand.